Good day, doctor. My name is Ambrose Ting Loong, matrix number 24302050. Experiment group T6A, partner's name Putri Mirza. Putri Mirza Mohaimin bin Zubir. Today I will be presenting my Viva and presentation. For your information, I'll be referring to the questions to the left, which is my laptop screen. So I will be looking at the camera and my laptop at the same time. Okay, the overview of the experiment, we've managed to perform these experiments in 2 days. In day one, we managed to get the experiment data for range and its maximum height. After that, we are able to perform calculations of error of propagation, and we've also successfully determined the relationship between h and its angle of projection, and range s and its angle of projection as well. After that, we've determined the value of gravitational acceleration and also its standard error via some linear laws, and we've plotted v0 squared sine 2 phi against s, and the other one is h against v naught squared sine squared phi. So after that, we've get our value around 8 point something meters per second squared. It is around the theoretical value, and the percentage discrepancy is around 16%. So the data indicate that the experiment has minor errors. And throughout this experiment, we've managed to complete all the 4 objectives, which is to determine the functions and also estimate the gravitational acceleration, the value of it. Okay, question A. What do you think the best angle of projection to start the experiment with? I think the best angle of projection to start the experiment with is around 25 degrees because of 2 reasons. To fully grasp the tendency of change of h, we should progress ascendingly, because as the results indicate, the higher the degree, the higher the maximum height. And by starting with a low degree, we are able to find out the ascending relationship between the angle of projection and also the maximum height. The second reason is that according to the maximum, according to the formula of S, which is v naught squared sine 2 theta divided by g, we can see that the sine 2 theta indicates that from 0 to 90 degrees, it's a half cycle. So by starting with 25 degrees, which is a lower degree, and we progress to, let's say, a higher degree, 85, 90, we are not only finding out how the projectile motion work, we can also determine the relationship between each corresponding angles, and we can, throughout the process, find out that the height of corresponding angles, for example 25 degrees to 65 degrees, are theoretically the same, and we can use experiment to back it up, although there are some minor errors and the values will not be completely the same, but we can see that there are a lot of similarities between values of S with its corresponding values. Suggest a way to accurately measure the height of projection of the steel ball. I think the best way to modify the experimental setup given is to move the vertical ruler closer to the maximum height of the steel ball. So what I would suggest is that to test to project the steel ball first, see at which position will the steel ball at any given angle or any degree of any degree of initial velocity, the position of maximum height. So if we move the vertical ruler closer to the maximum height, we are actually able to find out the maximum height easier, because throughout the experiment, the problem that we've encountered is that a lot of times when the position of the projectile that reaches its maximum height is too far away from the ruler, so it's very hard for us to determine the maximum height of the projectile, which is a steel ball. Suggest a way to determine the time taken for the projectile in this experiment to reach the maximum height. I would suggest using a high resolution camera that is attached parallelly to the ruler. So in this case, we are able to not the ruler, sorry, to the projectile path. So we are able to observe concisely at what time interval, at what point will that projectile reach its maximum height. We can pause and play to determine the actual time of the steel ball reaching the maximum height. From the theoretical physics point of view, will the type of material of ball affect the range and height of projection? I have two answers actually. Yes, if we are taking air resistance into account, and no, if we are not taking air resistance into account. My explanation, which is the answer to question E, is this. Yes, it affects, because of the fact that air resistance depends on the ball's surface area. So a different material indicates that it has different density. So given the fact that air resistance depends on surface area, let's picture using the example steel ball and wooden ball. So when the steel ball and the wooden ball have the same size, i.e. the same surface area, we will expect the wooden ball to have less range compared to the steel ball, because of air resistance have much higher effect in drag force that is exerted onto the wooden ball, because its mass is lighter given the same size. However, if we take a wooden ball that is the same weight, same mass as the steel ball, now that the wooden ball will be bigger, and the surface area will always be bigger, and as of right now, it will experience a higher magnitude of drag force. So that's why I said yes in the first place. But when I say no is when air resistance is not taken into account, because ideal projectile motions always assume there's no air resistance. Hence, all objects, they fall on the same rate, and of course its projectile motion is a perfect parabola. And due to this fact, and if we look into the theoretical equations or kinematic equations that we've derived in the lab report, the mass component is cancelled out during the derivation, and the final expression of S and H does not include mass, and does not include density, does not include surface area. So theoretically, it doesn't matter. However, if we're taking into account air resistance, it does matter. It does deviate the result. Okay, so I think I've answered all the questions. Thank you, doctor, for listening.